Alright, so this is the Unit 2 questions that I'm working through, the frequently asked questions parts. So we'll just get started, I guess. I'll draw pictures up here. So what I'm going to do here is write those given values that they give you, that F is always equal to 10 newtons, right? Capital M is always equal to 1 kilogram, and our coefficient of friction, should we need it, is 0.2. And on all of them, right, we're looking for acceleration of the blocks and the tension in the rope. Great. So, our first problem, which was number 2 actually in the packet, right? We have a block M connected to another block of mass 2m and a force F pulling to the right, right? So, first step in any good old Unit 2 problem is to draw Freebody diagrams. So I guess I'll make this block 1 and this block 2. So our Freebody diagram for block 1, right, we just have gravity pulling down, normal force pulling up, and the rope, the tension in the rope pulling to the right, right? So gravity pulling down, normal force pulling up, tension pulling to the right. And for block 2, gravity, right, normal force, tension pulling left, the rope pulling right. Gravity pulling down, normal force pulling up, labeling. Gravity. Tension pulling to the right, the rope pulls this block to the right, our force F pulling to the right, tension to the left. Alright, Freebody diagrams are done. Next step is writing sum of forces equations, right? And we're only really concerned about the x direction here, right? Nothing interesting is happening in the y direction. So the net force on block 1 in the x direction. Block 1, we are looking for acceleration, right? We're assuming they're accelerating. So our net force is not equal to 0, it's equal to ma. Mass of block 1 times acceleration of block 1, right? But our mass of block 1 we already know is capital M, or 1 kilogram, right? And we're looking at, for some acceleration, a1, right? Block 1 has a1 acceleration. And what's that actually equal to? Well, the only force we have is Ft, right, in the positive direction. So that's just equal to Ft. That's the only net. That's the only force we have. Then we have sum of forces for block 2 in the x direction. This one's also accelerating, so it's equal to ma. But in this case, our mass of block 2 is 2m times some acceleration a2. Right? And for this one, we have force F in the positive direction and Ft in the negative. F minus Ft. Great. We obviously can't solve these independently. We need to work together with them because we don't know two variables in each of these. So the first immediately obvious one would be, these tension forces are equal, right? It's the same rope, so the tension forces are equal. So you could take this and plug it in here as your first step. But it's actually really, really easy, and this problem, it would work fine with you. But it's actually really, really easy to make little errors with signs with these equations. Excuse me, hiccups. And so what I would recommend instead is figuring out the acceleration relationship, because these two accelerations are related to each other, and then plugging in from there. So I'll show you what I mean by that. So this block, right, is being pulled along, and then the rope connecting to this block, it's pulling them along at the same speed, right? So these blocks are accelerating equally, right? As much as this one accelerates, so does this one. So these, and they're in the same direction. They're both positive direction is what we said, the right direction, right? So A1 is equal to A2. In fact, I'll just call them both A, right? Because they're both the same thing. So these two are equal, meaning we could plug in here. And I'm going to do that because it's going to be more consistent on following problems. So I'm going to solve this one for A, right? So if we solve for A, it would just be A equals Ft divided by M, right? Straightforward. And then I'm going to plug this in to our A here, since it's the same A. 2M times what we plugged in for A, Ft over M. And that's equal to F minus Ft. Then we can just solve, because we know M, we know F, so we can solve for Ft. The M's go away here, and then it's 2Ft, so we can add this Ft over and get 3Ft is equal to F but I'm just going to plug in to save myself some board space. F is equal to 10 newtons, right? So to solve for Ft, just divide by 3, and Ft equals 3.3 newtons. That's the first thing we're solving for. We also need acceleration, right? Acceleration is easy to solve for here, though, right? Because in this formula, well, I guess this even right here, right? A equals Ft over m. We know Ft now. We know m already. So A is equal to Ft, which is 3.3 newtons, divided by m, our mass, 1 kilogram, just 3.3. Yeah, pretty straightforward. Meters per second squared. So that's our acceleration. Easy peasy. That's all for our first one, number 2/number 1, whatever you want to call it. So I'll erase and we can go to the next one, which is number 5. Those are, of course, 3.33 beating, right? But I just rounded 3.3. Great. I'll leave those values there because they're the same for each problem. Number 5 had this pulley right here. A mass connected to another mass, this one of 2m, right? This one is, oh, that's an n. This one's m, this one's 2m, or something like that. First step, as usual, free body diagrams, block 1, block 2. So our free body diagram for block 1, just gravity pulling down, right, and tension pulling up. So the force of gravity acting down, the force of, here we go, there you go, force of tension pulling up. Block 2, same thing, right, just gravity pulling down, tension pulling up. 2. Gravity pulling down, tension pulling up. Great. Step 2 is just free body diagram, or sorry, step 1 was free body diagram. Step 2 is sum of forces, right? And it's only the y direction here, right? Nothing even going on in the x direction. Sum of forces of block 1, they are accelerating, so this is equal to ma. Block 1 has mass m, so I'll put that capital M here. Accelerating with acceleration y-a-i. Acceleration 1, A1. So again, these accelerations are going to be related once more, but go ahead and write A1 and A2 until you figure that out so that you make sure you're getting your signs and stuff right. Trust me on that. So block 1, right, we have tension in the positive direction, gravity in the negative direction. Ft minus, this would be the force of gravity on block 1, right? But go ahead and plug in how you would calculate that here, because it's going to save you some struggles if you forget to do that. So this would be the force of gravity on block 1, but how do we calculate the force of gravity, right? Fg just equals to mass times gravity. Force of gravity is equal to mass times acceleration due to gravity. So our mass of block 1 is capital M times g, acceleration due to gravity, right? Because this is how, basically, Fg on block 1 is equal to the mass of block 1, which is capital M times g, right? So I just took, this is what this would go, so I'm just plugging that in there, right? Great. So then we write the net force for block 2. Block 2 is also accelerating, right? So it's equal to ma, but our m here is 2 capital M times acceleration of block 2. Same formula here, right? Tension in the positive, gravity in the negative. Ft is positive, minus the force of gravity on block 2, still equal to mg right here, but our mass is 2m. So write this out, force of gravity acting on block 2 is equal to our mass of block 2, which is 2m, times g, right? So here is a 2mg. All right. Again, these tensions are the same. So you could plug those in, but I'm going to make sure that we have our acceleration relationship down first so that we don't make any mistakes there. So let's look at the motion here that we would expect to happen, right? So this block is heavier than this one. So what's going to happen when they're released? Well, this one's going to go down, right? And this one's going to go up. So they're going to move like this. And they're connected by a rope again. So the accelerations are going to be equal, but they're just in different directions, right? A1 is positive, A2 is negative. They're equal but opposite. So A1 is equal to negative A2, right? Equal but in opposite directions. So we can plug things in for that. I'm gonna do that first, I guess. So I'm going to change these equations first so that we can plug things in with them. Actually, I don't need to change that. So I'm going to take the A1, well, A1 is equal to negative A2. So if I slap a negative sign here on this one, then that's right? I can make both of these A, but this one is negative, right? A1 is positive, A2 would be negative. So now we're ready to plug things in. I'm going to solve this one for A and then plug in here. But to save myself a little board space, right, it would just be dividing by M, right? So A would equal FT minus mg over M, right? And then I can plug that into A. So I'm going to cut down on my steps here. So negative 2M, don't forget that negative, we just wrote that, times A. What is A equal to? It's equal to FT minus mg over M, right? Because that's what you would get solving for A here. And that's equal to FT minus 2mg. Great, and we can solve because we know M, we know G. G is just 9.8, right? So we can solve for FT. These M's go away though, and we're left with negative 2FT. I'll just write that out. Negative 2FT plus 2mg is equal to FT minus 2mg. And just to move some things around, right? Add 2mg, add 2ft, so we get 4mg is equal to 3ft. And then we can just solve, right? Because we know m, we know g. This is just, I'll move the 3 over here already, right? M is 1 kilogram, g is 9.8 meters per second squared, is equal to ft. You do this math, 4/3 times 9.8. Let me do that. 4 divided by 3 times 9.8 is 13.0667, whatever. So 13.1 newtons. That's our FT. Then we also need acceleration, right? So just plug it in back up here again, say in the first one. So MA is equal to FT minus mg. So mass, 1 kilogram, times acceleration A is equal to FT, which is 13.1 newtons, minus mg, 1 kilogram, times 9.8 meters per second squared. That's just this equation here, right, plugging in FT and solving. So that's 1 kilogram. So basically it's 13.1 minus 9.8, right? So A is equal to 3.267, just 3.3 even. I'll just write that. Meters per second squared. Boom. 3.3 again, wow. Great. So that's problem 5. 13.1, 3.3. The next one is problem 10. Problem 10 has friction in it. So I hope you remembered the fun equation. Alright. Number 10. It looks like this. A block up here of mass m. A block hanging down of mass 2m. Like that, sorry. So block 1, block 2. First step, Freebody diagrams. For block 1, we have gravity, normal force, and then tension. Force of gravity, normal force, then tension pulling to the right. Ta-da. For number 2, in this case, it's just hanging down, right? So we just have gravity and then tension. Force of gravity, force of tension. Great. Oh, I nearly forgot, right? We do have friction here on this problem. Number 10 says coefficient of friction, mu. So in this case, there is friction here, so we do have a force of friction. Let me move this label to the left here, FF. We do have friction here. So a friction force to the left. Great. So obviously for block 1, we are mostly concerned about the x direction forces here, and for block 2 we're just concerned about the y, because that's the only important direction. But the x direction for block 1 has friction, right? Which we don't know. We have the coefficient of friction, but we don't know the friction force. So what we need to do is the y direction, right? So we can figure out normal force, use coefficient of friction to find friction forces. So we actually do have to do the y direction sum of forces first. So that's what we're starting for block 1, with the net force on block 1 in the y direction. In the y direction here, right, it's not accelerating, right, it's staying on the surface. So our net force in this case is equal to 0. And what do we have? We have normal force in the positive, gravity in the negative, right? Normal force in the positive minus force of gravity, right? But force of gravity is mg, and this one's m is just capital M, 1 capital M times g, right? So we can plug in for mg and solve. Our mass is 1 though, right? M is equal to 1 kilogram, g is 9.8. So easy maths here. Our normal force is just 9.8 newtons. Great. So we can use this to figure out friction force, right? Using the fun equation. Friction force is equal to mu times the normal force, Fun. Friction force is what we're solving for. We know these two, right? 0.2 times 9.8 newtons. 9.8 times 0.2. Friction force is 1.96 newtons. Great. So now is where we can successfully use the x direction net force right here. So now we start basically where we left off with the other ones, where we can do just the x direction on this one. Net force 1 in the x direction. It is accelerating in the x, right? So it's ma, mass is capital M for block 1. We have tension in the positive direction, friction in the negative direction. Force of tension minus the force of friction. And we can't go any further here, right? This is A1, right? A1. So we can't go any further with this because we don't know A1 and we don't know FT. So we need to write the net force for the block 2. It's in the y direction, but that's the only direction we're concerned about here. It is accelerating, so it's equal to ma. Our mass is 2m. And it's accelerating A2. So we have tension in the positive, gravity in the negative. This is the force of gravity on block 2, right? So mass times acceleration due to gravity. Our mass in this case is 2m times g. All right. So what's our acceleration relationship? Well, obviously they're connected by a string, so accelerations are equal. But block A is to the right, which is the positive direction, and block 2 is in the negative direction. So they're equal, but opposite once again. So A1 is equal to negative A2. So I'm going to do this the same way I did the previous one, which is just to slap a negative sign there and erase these. Great. So then we just solve this one for A, and to plug in here. It's equal, fortunately, to the same thing that it was before. So negative 2m is equal to just ft minus ff divided by m, right? Because that's what you would get here if you solve for A. Equal to ft minus 2mg. So we know ff, we know mg. We can solve for force of tension. These m's cancel. Negative 2ft plus 2ff equal to ft minus 2mg. We can move this ft over, move this mg over, and what you would get is 3ft, right, is equal to 2ff plus 2mg. I just flip-flop this. Obviously it would be written the other way, but so we know force of friction, we know mg. I'm running out of board space, so I'm going to plug in here. Our force of friction is 1.96 newtons, right? Plus 2, m is 1, g is 9.8. So we have 2 times 1.96 plus 2 times 9.8, which is 23.52, and then we need to divide by 3, right? Because this would be over here. Divide by 3. So our force of tension is 7.84 newtons is what I have gotten. 7.84 newtons for Ft. I'm obviously very, very low on space here on the board. Now, I just double checked the book answer because I thought I remembered something being different here. The book answer that you guys got was 8 newtons. I believe that's just because they just used 10 for gravity. So if you use 10 for gravity, you would get 8 here. My suspicion was correct. I knew that this was where I was supposed to talk about something. So yeah, that's why the book answer would be 8, or if you use 10, you would get 8 here. But I got 7.84 because I used 9.8. So that's our tension. We've got that. We just have to plug in here, right, to get acceleration, our other value, much like the previous ones. I'm going to do that over here, I guess. M is 1 kilogram. Okay, is what we're solving for, equal to tension force, which is 7.84 newtons in my case, minus force of friction 1.96. So acceleration is equal to 5.88 meters per second squared, or I believe it just gave you a flat 6, right, if you used 10. In my case, 5.88, 7.84. In the book's case, 8 and 6. Lovely. Last but not least, we have number 10. Or that was number 10, or 12. Did I say number 12? I don't know. Number 12. Number 12. Number 12 actually ends up being a lot like, which one is it? Number 5, actually. So this mass over here is 3m connected to a mass over here, which is just m. Okay, Freebody diagrams. 1, 2. Freebody diagram of block 1. Just gravity down, tension up, right? Gravity down, tension up. 1, 2. Same thing for number 2, right? Gravity down, tension up. Great. Freebody diagrams are done. That means net force. Net force on 1. For block 1, right, our mass is 3m times A1. Just tension up, gravity down, right? Force of tension minus our force of gravity, which is just mg, but our mass here is 3m times g. Net force of block 2. ma, right? But our mass here is just m times a2. Force of tension in the positive minus force of gravity down, right? But our mass here is just m times g. All right. The next one, right, is our acceleration relationship. So this one's 3m and this one's m. So which way would we expect it to move, right? This one's going to go down. This one's going to go up. So a1 is negative. They're equal, obviously, again, with a straight connection, right? So a1 is negative this time, and a2 is positive. So again, I'm going to fix this the same way I did before, right? Which is just slapping a negative sign right here, because a1 is negative, a2 is positive. So now I can solve for a and plug in, right? So again, I'll just divide m here so that it's ft minus mg over m, and then plug into this equation. But trying to save board space, so negative 3m times a is ft minus mg divided by m, right? Solving for it here. is equal to ft minus 3 mg. So I know m, I know g, I can solve for ft. Same solutions, similar here, right? M's go away, minus 3 ft plus 3 mg is equal to ft minus 3 mg. So I can just move the ft over, move the mg over, right? So that I would get 4 ft is equal to 6 mg. And I know mg, so if I just move this 4 over here, right? So divide by 4, this would simplify to 3/2 times m, which is 1 kilogram, times g, which is 9.8, in my case, meters per second squared. Sure. So it's really just 3/2 times 9.8, or I guess if you use 10, right? Which in my case, 1.5 times 9.8. ft is 14.7 newtons. If you use 10, that would be 15, right? For me, 14.7 for attention. Then just plugging in back here for acceleration. So m is 1 kilogram. A is what we're solving for, is equal to ft, which we just solved for, which is 14.7 newtons, minus mg. Boom. Basically, since this is just 1 kilogram, we're just 14.7 minus 9.8. So for me, acceleration is 4.9 meters per second squared. For you, if you use 10, where in the book, it is just 5 flat. Lovely. So that's 12. Any further questions? I can break things down further if you are confused. But that's all. That's number 12. That's the last one. Bye.